What's the connection between this plane with the vector normal to it and this equation? Well, we call this plane the solution plane to the equation. And the reason we do that is simply because all the values of x, y, and z, which are connected by this equation, can be represented as points on that plane. And that's why we call it the solution plane. Now, later on in the program, we're going to be looking at several equations like this, each represented by planes. And so we're going to have the problem of looking at several planes at the same time. But before we go into that, let's have a more detailed look at this particular equation. The first thing to notice is that it's a linear equation in x, y, and z. In other words, we don't get any x squared terms or y squared terms and so on, no yz's or xz's. The variables x, y, and z appear just like this. And what that means is that we can write this equation in matrix form. We can write the coefficients 2, 3, 6 as a row matrix, the variables x, y, z as a column matrix, and the equation just takes the form of that matrix product equal to 21. And we can take that a step further as well, because this row matrix we could think of as a vector in R3, just written in row form. If we call that vector A, then that's the vector written in row form. And we could also think of this as a vector in R3, and we'll call that one X. Now, you should remember that matrix multiplication is effectively just a question of taking dot products of rows and columns. So now we've got this vector representation, we can rewrite the matrix equation in a pure vector form, because we can replace 2, 3, 6 by the vector A, and then the matrix product times x, y, z equal 21 just becomes A dot x equals 21. In other words, we can rewrite our linear equation as the dot product of two vectors. And it turns out that the vector we saw earlier is A, and the set of vectors x which fit the equation specifies the set of points which lie in the plane P. And what's more, the vector A is perpendicular to the plane. Now, this representation of a linear equation in three unknowns by a plane in R3 is quite remarkable, and it's a very useful visualization. And it's this that we're going to use to build on in the rest of the program. So, first of all, let's try to justify this picture we have for this particular equation. Remember, the coefficient vector is 2, 3, 6, and P is the plane representing the solution set. Now, the easiest way to see the connection between the equation and the plane is, in fact, not to look at this problem, but to look at another one. It's quite a familiar sort of mathematical technique. To get some insight into a particular problem, you look at one that's closely connected, but simpler. And what we're going to do in this case is to look at a very similar equation, the one you get just by replacing this right-hand side by 0. You see, this is a very similar equation, but much simpler. And the effect on the vector equation is just to make it take that form, a dot x equals 0. And now you can see why we've done that, why we've chosen a simpler form, because this is a condition on x that we can interpret very easily, because all this tells us is that the vector x must be perpendicular to orthogonal to the vector a. And since we're dealing with vectors in R3, we can just picture a and x as two vectors at right angles. These are just three of the set of all vectors x orthogonal to the coefficient vector a. This set, in fact, specifies a plane through the origin at right angles to the coefficient vector. We've called this plane H to remind us that it's the solution plane of the homogeneous equation. So far then we've got this homogeneous plane, which is the solution plane for the homogeneous equation, right-hand side equal to naught. The plane passes through the origin, so it's a subspace of R3, subspace of dimension 2. The only trouble is, remember that the particular case that we're dealing with is not homogeneous. We didn't have a right-hand side equal to 0. If you remember, we had a right-hand side that was equal to 21. This was our original equation. That means that the vector form of the equation takes this form, a dot x equal 21. And what we've got to do is to use our information about the homogeneous case to tackle this one. So let's first of all just remind ourselves of what this dot product really means. Remember that a dot x simply means the length of the vector a multiplied by the length of the projection of x onto a. You see, the projection of x onto a is a vector q. So a dot x is the length of a times the length of q. But remember, a dot x is 21. So the length of a times the length of q is 21. And actually, the length of a turns out to be 7. You can check that for yourself. We just know it from its coordinates. And that means that the length of q must be 3. So any vector x which satisfies the equation a dot x equals 21 must have a projection onto a of length 3. Can you see that the solution set lies on the plane P at right angles to A? So this plane must be parallel to the homogeneous solution represented by the plane H. So what have we seen so far? We've seen that a linear equation in 3 unknowns can be represented by a plane in R3, like this plane P. And that, in turn, is parallel to the homogeneous plane, which represents the homogeneous equation. And because the coefficients of each of these equations is the same, each of these planes are in turn parallel and normal to the same coefficient vector. Now let's look more closely at the connection between the homogeneous plane H and the general solution plane P. Remember, they both have the same coefficient vector, but for now let's forget about that and think only about the vector which separates the planes. Call it Q. Now, a point in the general solution set P is specified by the vector V. And another vector U specifies the corresponding point in the homogeneous solution set. V is the vector sum of U and Q. So what we've seen so far is first that we can represent a linear equation in 3 unknowns by a plane in R3. And we've seen that the homogeneous equation is represented by a plane through the origin, a subspace. And changing the right-hand side, making it non-zero, gives you planes parallel to that subspace. What we're going to do now is to complicate the issue by introducing some more equations. Here's Robin.
What Norman's just shown you is a very useful way of thinking about equations, representing a linear equation in 3 unknowns as a plane. And what I want to do now is to see what happens when we bring in a second equation.
These planes represent 2 equations. Each equation is represented by a plane. Clearly, the solution set in this case is represented by the line L. Now the homogeneous pair of equations both pass through the origin. This means, of course, that their solution set is the line H, also through the origin. Now the solution planes are parallel to the homogeneous planes, so that the solution set L is parallel to the solution set H. Take any elements u in the homogeneous solution set H, add it to the vector q, and this will specify an element v in the solution set L. In this case, v equals q plus u. So there's a one-to-one correspondence between elements in H and elements in L.
So we've now dealt with the problem of the two equations, and we looked at the solution set in some detail. But what I want to do now is to go on to a third equation. What happens when we have three equations in three unknowns? And that's a situation you've met several times already in the text.
These are the planes you just saw corresponding to two equations giving a line solution set. And we now add another plane corresponding to a third equation. Clearly, in this case, the solution set is just a point, the point of intersection of all three planes. But is this always the case?
Well, you can see that there must be exceptions just by thinking geometrically. For example, take these two planes. These are parallel, so there's no point in common to the two planes. What that means is that the equations that they represent can't have a solution. The solution set of the equations must be empty. Well, what does that mean algebraically? These are the equations of the two planes. One is the plane P that we've been talking about frequently, and this is the equation of the other plane, Q. And the thing to spot about them is that the coefficients are the same. In other words, these two equations have the same coefficient vectors, and that's why they're parallel. The only difference in the equations is the right-hand side. The bigger that right-hand side, the further away from the origin is the plane. So let's introduce another equation to see if we can get a solution. Let's have a look at this one. Now this time you see the coefficients are each twice the coefficients in P or Q. And so the coefficient vector for the plane R must be twice that for the planes P and Q. So these equations just represent three parallel planes. So really the case of parallel planes is quite easy to tie up algebraically, because you can spot parallel planes because the coefficient vectors must either be the same or just a straightforward linear multiple, one or the other. There's one small point, though, that we ought to tidy up, and it's this. You see, the coefficient vector does determine the orientation of the plane, but not its position. The position is determined by the right-hand side, and it may so happen that the right-hand side just gives you a value that makes the planes not only parallel, but actually coincident. And of course, what you're getting there is perhaps two equations representing the same plane. Well, don't worry too much about it, because it's only a technical problem, and we've cleared it up in the text. Anyway, let's press on with this. Let's see if we can get a solution by changing another one of these planes. Let's change this equation Q to see if we can get a solution. Let's have a look at that one. This time, you see, Q is not parallel to P or R, but although this time Q is not parallel to either P or R, there's still no solution, because there's still no point common to each plane. Well, of course, you'd expect that because we still had two parallel planes, and in fact, you could have spotted it easily enough just by looking at the matrix of coefficients, because you've got this third row as a linear multiple of the first. But we could change R like this to try to get a solution, and this time we get three non-parallel planes, but you see there's still an empty solution set. There's still no point common to all three planes. Well, this time it's not at all obvious just by looking at the equations that you haven't got a solution. So let's see what happens if we keep the same coefficient vectors and move one of the planes parallel to itself. See if we get a solution this time. By moving Q parallel to itself, you see, we can get a solution, but not a single point solution. We get a whole line of solutions. Let's just see that again. This time, look at the associated matrix equation at the same time. Look particularly at the right-hand side of the equation. You see, we've got a problem. We can't tell just by looking at the left-hand sides whether we've got this situation or this one, because the only difference is in this right-hand side here. To distinguish between these two cases, you see, it's no good just looking at the same left-hand side because they've got the same homogeneous form. What you've got to do is to look at the left-hand side and the right-hand side together. But first, let's look at that left-hand side again in a little bit more detail to see if we can get a clue. This is the homogeneous form, and they do have a solution set, a line through the origin. Remember when we first looked at a plane representing a solution set, we included the coefficient vector on the plane, and since then we've usually not included it, simply to make it easier to see the planes. Let's now go back to the planes representing our homogeneous set and put the coefficient vectors on and have a look at them more closely. It would seem that the vectors are coplanar. And we already know that if three vectors are coplanar, then they must be linearly dependent. In other words, one of these vectors is a linear combination of the other two. What does that mean then in terms of our matrices? Well, the rows of the matrix are essentially just the coefficient vectors, and so the first row is the coefficient vector A, and the second row is the coefficient vector B. And it turns out, and you can check this for yourself, that the third row can be expressed as a linear combination of the first two. C is just 5A minus 2B. And now we're in a position to distinguish between these two cases. Because you see, if the right-hand sides of these equations are in the same linear combination as the left-hand side, then essentially one of these equations is just a linear combination of the other two and is giving you no extra information. And all the information is contained by two equations, in other words, can be represented by two planes, and the solution set is just the line of intersection of those two planes. So you see, now we're in a situation where we can analyze any case of linear equations. We can get various things arise. We can have a point solution set, no solutions, a line of solutions, or even a whole plane of solutions. But it's interesting to notice that they do separate into two classes. You get a single point solution only if the coefficient vectors are linearly independent. And all the other cases arise when the coefficient vectors form a linearly dependent set.
glued